Hey guys, welcome. We are starting the Cloud Genius Machine Learning and AI Bootcamp, which is described in our website here. You can probably see that one at this location. And what I will like to do is, for those of you who are familiar with Cloud Genius, you probably know that we have, those of you taken the Cloud Bootcamp, like the one that you have before, we have recorded videos and we have a material already written down. Whereas in the Machine Learning Bootcamp, we are doing it live in terms of exercises that we will be focusing on using a textbook. So the book we intend to use is this book. There is a required textbook here, that ISBN number. And so if you take that ISBN number and go to a Google search or go to Amazon, things like that. So here is the book. Like O'Reilly sells it on, I think they sell it on Amazon maybe, and a bunch of other places you can actually buy this book. Your company might have access to this book through online subscription or other places. So if you go to Amazon, you should be able to find the book right there. And I prefer a book in electronic form as opposed to, so right there, there's the book. I prefer it in electronic form for the reason is that this particular book, and you can of course save with coupon or something like that, and this book is updating itself. In fact, it will soon update to version 2 of TensorFlow, and so this is the first edition. It has a little bit of updates that have already been pushed, and the second edition is coming up in next year. So I spoke with the author of the book and confirmed with him that the book is not available for early access. So there is this book available, and we can, of course, order that book. And in fact, I will pre-order it. And so the whole idea behind this will be that we...
Hello.
Hey, hi. Is that Ishan there?
Yep. Hey, this is Ishan.
Hi.
How are you guys?
And so we have Troy, we have a couple other people also join in, and we have people who are not on the conference. They are watching it offline asynchronously based on the recordings that we'll be doing. So that's what I wanted to say is what I also got a message from Ishan that he wants to go today for some session or something else. So he's not able to join is what I hear from Ishan. So Ishan, you can hang up and go if you like.
Okay.
But I will have the recording, and recording will become available here somewhere. I'll tell you exactly where I'll put it. And that recording will pop up in the website. You should be able to access it.
Okay.
Okay.
Sounds good.
Yep. Thank you. Thank you. Bye-bye. So let's begin. What I want to do is make sure that you have access to the book, which I guess you have. And one thing I would like to also point out to you is that this book has an accompanying Git repository. And that is something that you should be familiar with. And I'll pull it up right now. So go to, I think the best way to search is hands-on machine learning. That's the keyword to search. And you will automatically land on the Git repository for the book. Now this is a fairly comprehensive repository containing solutions to every single problem mentioned in the book. And that is what I will be going through primarily to the extent it is feasible to fit. And we'll of course pick and choose the areas of your and our interest. And hey, somebody just joined. Is that Chris? Or he's coming online, I guess. So yeah, he's still muted.
Yep.
So hey Chris, how are you doing?
Pretty good.
Good to see you. I mean, not actually seeing you yet, but yeah, but I understand. And so we just began, and I am making sure that I'm recording these videos and that I will be making them available on this website. I'll tell you exactly where I'll put it. But the focus that we have in this bootcamp is that we are using a textbook, and it has a Git repository that goes with every single exercise in the book is already available to us. And this person who wrote the book, this guy, his name is Aurelian Giron. I don't know how to say this name, but I know him. He is in my network. He used to be at Google. He used to be the person who was in charge of classification of videos in YouTube. And he, I think, runs his own company these days and runs machine learning practice. So that's a fairly popular book. And that book is here, which I just added a second edition into my into my shopping cart, and I'll probably check it out, but that's for future. That book, second edition, is coming up, I think, in the month of May next year. So he's not available right now. I asked him for a pre-release, and he's not ready with that yet, because I think the thing that will be in that second edition book will be the version 2.0 software for TensorFlow. So in our bootcamp, we will be focusing on two different libraries. These two libraries are the scikit-learn library and TensorFlow library. Both of these libraries, let's go look at them. Scikit, this library is based on Python. It is an open source project. And what I would like to say is that this project think of it as like a Swiss Army knife. It has a comprehensive collection of all the algorithms that are known to mankind, and they have implemented it to the best possible mode of implementation. They use Python, and in certain cases, they will also have low-level C implementation, and the libraries are ready for us to consume. So we'll use these libraries quite a bit. We'll also focus on the second library, which is TensorFlow, which is also open source. TensorFlow is this product. This became open source, I think, a couple of years ago. It is at 1.10 version right now. It is an open source framework for machine learning, but a dedicated focus of this particular toolkit is in deep learning. And deep learning, I actually would like to say that there is nothing deep about deep learning. Figuratively saying, it basically means that there are layers of I would say, I don't want to use lingo without introducing it, but there are multiple layers of computation that happen before you get to the result. And so that is why it is called deep. That's the only reason that I can come up with that makes sense to me. There are various meanings behind the word deep learning, and we'll talk about that later time when we start discussing TensorFlow. But the goal is to, or TensorFlow, the goal is to focus on what is machine learning, what are the various possible scenarios we can use it and get to use it. We'll kind of sort of follow this book itself, which I have here right now, which is the book that I was referring to, which is Hands-on Machine Learning with Scikit-learn and TensorFlow 2 libraries. And we will basically begin using this book. We'll also take digressions into understanding some of the basics that are necessary, some basic math, not too much math, but there is going to be some math and some theory for us to understand concepts, but only as necessary. That's what I would like to do, is not go too much into theoretical discussions, but instead take a step back and apply in terms of what does it make to use this in the context of solving a problem. And so let's begin with identifying what is machine learning. And the best place that I typically go and ask that question is to Wikipedia. That's my habit. Anything that I do not know or want to get an authoritative answer, as long as it is not political in nature, I usually go to Wikipedia. It's a very good encyclopedia, as you know already. So let's go read the definition itself. And here is the definition in the first few lines. In 3 words, if I can describe what is machine learning, I would say the 3 words are learning from data. That's how I would look at it. So if you look at this picture, you have some data on a graph, and you want to learn to partition, to separate, to decide, to make inferences, whether it is a filled dot or an empty dot. You come up with some kind of a function. Maybe it is represented mathematically, maybe it is not represented mathematically, maybe it is a straight line like this, maybe it is not a straight line, to make a decision function between a black dot versus an empty dot. And such decision making is done by studying the data itself. So now if you look at the concept of the things that are necessary for machine learning and artificial intelligence to happen, is that we need to have certain things available to us at our disposal. And those things are that, first of all, there is a pattern to something. There has to be a pattern of some sort. It doesn't have to be simple or complex, or any pattern. That if there is no pattern at all, if it is purely random, then it is pure random. Then it is not a scenario when we can actually apply machine learning techniques or artificial intelligence technique to understand and to solve a problem or to make a judgment or make an inference. You cannot do that because we know by definition it is purely random, right? So if it is random, it is random. The answer is going to be random. So that is not what we focus on when there is a pattern of some sorts. Second, when we cannot express it mathematically in simple terms, we cannot do a mathematical calculation and come up with an answer. So math is not, a mathematical representation is not easily possible. A representation is missing, let's say missing. And third one, that you have data. If these three things apply, then we can apply techniques, or I would say algorithms, to make use of computers in the context of what we have in our desk or our laptop, or maybe if there is a bigger problem and we need bigger horsepower, we can actually access the cloud to solve these prediction problems, inference problems, and come up with an answer to or a solution to a scenario that we are trying to find out how to solve. So these are the three things necessary, by the way. If there is no pattern and it is purely random, don't touch it. If you have no data, don't bother. I mean, it is learning from data. That's the key thing to remember. So we have to have data. We will come up with patterns to identify what does it take to make it happen, and then apply techniques. So with that understanding of a simple understanding of what conceptually machine learning is, let's go understand what does it actually do for us. How do we classify it? What are the variety of algorithms available? And then we will go do a mathematical digression to understand how do we actually use math to deal with the problems that we have. And so we will use this tool that I mentioned called on GitHub, that I should actually point out to you again, is that we have this library right here, which is hands-on machine learning library, which is this is a supplement to the book itself. And this is a series of Jupyter notebooks. And Jupyter is another open source project. So if you say Jupyter notebook, and you will find that this project is actually a derivative of the Iron Python project. And this is also open source. This Jupyter notebook runs Python in your web browser. As simple as this. So let's go see a quick look. Something like here. So it's going to open a notebook for me in the web browser. And here we can basically do whatever we feel like in this cell here, I will say, let's say there's some simple math, 2 plus 2. And then I write that down and evaluate, and I get the output right there. So see, it's like a calculator to be simply saying that, but what you write here in a cell is expressed as an output when you execute it. And so you can dynamically execute any Python or actually there are a variety of things you can actually run you can run Python. I think this one is designed to run Python, but you can run 3 more different languages. You can run R, you can run Scala, you can also run one more language. I'm forgetting what language. There are a couple of languages supported in Jupyter. So not here. In Jupyter, I think the language of choice, Julia. So Python, R, Julia, and Scala. These are the 4 languages built into Jupyter, and you can just execute that. To install Jupyter on a Linux or a Macintosh is fairly easy. To install it and get it to correctly work every single time on a Windows machine, I don't need to say it's not easy, but actually it is kind of clumsy, I would say. So to simplify that, what I have done is I have created a Docker image. You know Docker. Probably you don't. If you know Docker, you probably understand what I'm talking about. If not, we will go through these steps to make sure that you get Docker. And once you have Docker running on a Windows laptop or a Mac or Linux or whatever you have, then you can use an image that I have created, Cloud Genius image. It's called hands-on machine learning. And you can use this image to run, what is that? Okay, let's go say Docker And then you should find the image. Let's go to Docker Hub, I guess. So, but there is an image, Docker Hub, or hub.docker.com. That's where you will find the image. And you can just use it, pull it, and things of that nature. And that's where you will see that this kind of Jupyter notebook will start running in your laptop, in your desktop, Windows, Mac, Linux, whatever. And it will function with all the code that is necessary to run with our program. And that Docker image is available here. And we can freely download it. It's open source. And so you can see how it is built and all that. But let's get straight to the image. And so that image is available in the Cloud Genius repository as, where did it go? Hands-on. And hands-on. There it is. It was there. I saw it. So this image is fairly recent that I have created it 13 days ago. And it basically simplifies the running of Jupyter notebooks in a Windows machine if you want to use Windows. So you have to first get Docker and then get this image. And then you get to this point, which is where you will run Iron. I should not call it Iron Python anymore, because the new name of these notebooks is Jupyter. And so we'll be running those examples, exercises, hands-on exercises that are built in to support the book itself, and which is this book, or not this book, the book that I mentioned, which is here, the preface. And so we'll go through that, but first of all, understand as to what the outline of the program is going to be. That's what I want to basically go through, understand classification, understand what it means, how do we actually then apply Iron Python Jupyter notebooks to use the scikit-learn library first, and then TensorFlow libraries to handle a variety of problems. These are real-life problems with real-life data available in multiple data sources on the internet. And if you're using this in corporate scenario, make sure that you keep your data private. Don't share it with anybody else. If they are in your company, of course, you're free to share. If they're outside your company, make sure that you don't share your data. So keep that data that is private to you, keep it private. Don't discuss company-specific information with people in the group, in the class, in this, because it is a public class. I just want everybody to know that this is not your company's program. You are, of course, your company will be paying for it, but the idea is that this is a public program. Like, people from anywhere can join, and so please refrain from discussing company confidential material. If you really, really want to discuss it, do it in a one-on-one session with me. But again, don't tell me private information, because I am not in your company. So with that, let's begin. So this idea of machine learning, it is not new. The concept, it has been in place even when I was in college, like long time ago, 30 years, so 27, 30 years ago. So in those days, I actually wrote a program known as optical character recognition. You may have heard of this thing called OCR, and even these days there is OCR software available. You can probably see what OCR does. Let's see the best example of OCR. I think this one will give us some examples. And OCR is nothing great, these days, but it basically looks at what do you have that is printed or written down by hand. Hope not a doctor's handwriting, but it'll try to read and figure as to what is actually written, and will translate that in terms of alphanumeric sequences, characters. And that's basically OCR. That's what OCR is. And I tried to create such a program, and it sucked. Yes, big time sucked. And in fact, it was so bad that I gave up on the project, like the rest of the world did. It did not work. It did not successfully work exactly every single time. In fact, if you have a human being sit and look at a pattern of written text, printed text, the error rate of a human reading through some text and correctly predicting what is actually written down is fairly high. People can read just fine. Machines cannot. But these days, machines actually can read better than humans, which is kind of unbelievable. It is unbelievable because of the efficiencies accomplished through a variety of techniques, especially created by this person. His name is Jeffrey Hinton. And what he did is he wrote a paper on how to train a deep neural network uh, capable of recognizing handwritten digits. And so the accuracy that they were able to accomplish was more than 98%. On an average, if you have a person, a human being, look at written text or handwritten text, I should say, like, if you, in fact, there are databases that have images of numbers written by people in handwriting as they fill up envelope boxes with zip code. So 0 through 9, all the characters. Multiple people write these things by hand in their own handwriting, which can differ from person to person. And there is a gigantic database of all these digits. It's, I think, called MNIST database. So the database is MNIST. That's the name of the database itself, which has this bunch of numbers handwritten. And if you put a person in the job of actually correctly identifying what those images mean, like, and if I write 9 like this, it will actually be read as the number 9, or rather, even that is a bad handwriting. So you know what I'm talking about, the actual number 9, like this, 1999, that number. So that's what I'm talking about, is to accurately, correctly predict what that character is. Like, this is my bad handwriting, and this is my attempt at a decent handwriting. And so the result was that people, human beings, can come up with an accuracy of about 2.5% of mistakes. These are the mistakes that people will on an average do with a database called MNIST. However, this precision was more than 98%. And that technique that they use to develop a neural network, which is basically multi-layer network, and they branded it as deep learning because there are multiple layers and you can have any number of layers you like. And so it is giving you the perception of depth. And that's the reason why it was considered deep learning. And it has gained amazing popularity since those years, which is fairly recent, 2006, not that far away from us, from now. And that's when this thing called machine learning and artificial intelligence basically, came back to life in some sense. Now, if you look at it today, machine learning is everywhere. Everywhere, as in, you name it, it's there. You have, these things: Siri, Google, and Alexa, and all that. And I should not say the word Siri because I am surrounded with devices that will activate if I say it loud. And same with this. And I have all these guys, so they're here in my room, and I have muted them. But I hope they're going to keep quiet. So I will not use the action word to actually invoke them. But having said that, these things what I'm talking about. And that this is kind of, it's an average or below average product from a speech recognition perspective. This one is the best one that I know of. And this one is okay. And it has a bunch of applications. And, of course, all three have applications. And the idea here is to focus on understanding speech. And when I was at Microsoft I think it was like 17, 18 years ago, there used to be a team. The team was called Wreck a Nice Beach. That was the name of the team. The focus of that team was speech recognition. And so that was a play on words. It basically meant recognize speech. And when you say recognize speech, it will not actually recognize speech. I mean, it will not recognize the words you're saying. It will recognize something erratic and idiotic like this, for example. And so that was the scenario that, people used to make fun of older days, 20 years ago, 17 years ago. But today we have, this lady called Cortana, which is also in the same game. And they all play nicely in terms of understanding speech, understanding human speech, even if there is an Indian accent or a Chinese accent or one of those variety of accents that people have. They will be able to do a decent enough job in terms of understanding what the person is saying. And that is such a feat. I mean, we take it for granted these days. You look at the idea of understanding and learning from data, basically applying machine learning and AI techniques to everything that we do every single day. We look at web search results. We look at, just go to Gmail, for example. Let's go here and try to see if we have some spam in my inbox. And so you will see that I may or may not have some spam. Do I have any spam? No. But that classification works wonders, and really, really wonderfully. And so if you want to code such a thing, which will actually correctly classify whether an incoming mail is spam or not, that's the goal, right? In a project like that, the goal is to correctly detect whether an incoming mail that you have, so you have an inbound mail, and you have to make a decision whether this mail should be flagged as spam or ham. Ham is the word for good mail, just a word. Ham as opposed to spam. It's a word people use. Basically it means good, bad. That's what it means. And so you want to make that decision. And the core idea behind it is that you are basically making a binary choice. It's either this or that. It is a digital scenario. It's like flipping a bit. Either you're spam or you're not spam. And that's one class of problems when you are basically classifying good, bad. So these type of problems, when you're classifying, are called classification problems. So that's a group of problems that you typically end up doing such a thing, like good or bad, yes or no, disease or no disease, or things of that nature. Basically, it's a binary classification. And binary, as in there are two states, here and here. If you extend the same logic into multiple buckets of classification, then it is not a binary classification anymore. It just becomes multiple bucket classification without the word binary. An example of that would be back to our inbox. And you will see that sometimes you have these categories which have buckets of variety of types. For example, social media. So let's go look at social media. And so here are the emails that are already classified as social media, because emails coming from Meetup and YouTube and Facebook and all that, they're automatically classified and filed under social media. There are updates that I occasionally receive, or rather I should say emails I receive from systems that are sending emails are basically notifications or updates of some type. Like if I buy something, then I get a notification like this that I buy a jacket, and then that it automatically gets classified as a notification or an update. So it folds into this folder automatically. If I'm participating in a forum of some sorts, it gets folded into that forum folder. So here is a security vulnerability notification that came in from Farhana. And that security notification is people who are developers, they will occasionally receive. So I am one of the people that developed this software from EDX. It's another open source project. And so I receive those notifications, and those are part of the EDX forum. So they get classified already, just like this, automatically in a multi-level classification system, which is classifying incoming email, the good ones, into further buckets like social, notifications, or what was that, updates, and forums, like that. So you can have your own classification, and it will, over time, it will learn from your actions. Is the idea, whether it doesn't have a mind of its own, it has to learn from something. And so when it learns whether an email is spam or ham, somebody has to train the system. And that training involves almost like a supervisor sitting and telling and training the system, hey, this email that just came in, that should be good, or that should be bad email, or ham or spam. So that decision making needs some data from a supervisor, literally telling the machine learning system, this email is good, that email is bad. And that constitutes the data from which the system will then learn and figure out what is good, what is not good, and then attempt to classify any new coming email that come into the system and gets correctly labeled. So that is the binary classification that requires data from a supervisor. The supervisor is basically a person who knows whether an email is spam or not, a person who understands that this is a spam. And so let's go see if I can find a spammy email. I'll go and find out, and then you will see some junk, but that's unfortunate. Let's see if I have any spam right there. Let's see if you can find some spam. Yeah, there is a lot of, so let's go see one of those guys. Okay, let's see. Yeah, that's a good one. See, here, you have an email saying that somebody is going to deactivate my account. I mean, wow, come on. So yeah, this is, by the way, a spam. You already know that. And so the sender of email is, I don't know what this thing is, financial fines, God knows what that thing is. And so you have a person looking at, like, this sender is not valid. It claims to be Yahoo Mail, but the actual email address is different. It's going to me in my Yahoo inbox, and reply goes to some other debtor club, firearm, I don't know what. And so these are random locations the replies are going to, and it is telling me that my request to remove your account from Yahoo server is approved. And ignore this email to continue with email removal. If it is not you, please reply to us. So they're basically farming for an email or email address that is valid, so they can further spam me. That's the idea. But a human being who's smart enough and looks at this email and says, hey, this is spam, and that information needs to be labeled in form of data that correctly advises the system that this is spam. So then system will eventually learn from it and classify it as spam. By the way, these spam systems work so beautifully that I don't even have to go and look at in my inbox in the spam folder at all. In fact, I had to struggle to find this spam email just to talk about it. But the idea is that if you try to write these things in terms of code that looks at the characteristics of the sender, the reply to addresses, and the body of the message, and try to program it yourself, and you will come up with rules. For example, something like, let's see if I can give an example of that. Not here. So I'll show you in this piece of paper. So if you have a pattern, let's say here, that is kind of spam. Oh no, come back again. There we go. And so if you see these patterns coming from the subject line, my name, your account will be deactivated. If that's the pattern that you're looking at, you will try to program it and programmatically try to make a decision tree of some sorts to make an analysis without training. Like I'm talking about the scenario with learning from data versus the traditional old style approach, which is a decision-making system. So you have to make a decision, the system has to decide on its own without external training data. The machine has to learn from what is going on, whether this email should be considered spam or not. In that case, so 10 years back, 20 years back, if you now look at what people used to do is to make a decision whether a particular email is spam or not, we'll try to classify and actually decide whether a particular email contains, like, I have this word Nigeria. That's an old style example. Nigeria and the Nigerian prince. These words show up in the body of the message. So if you detect these words, then you will automatically create a procedure in which an email that contains the word Nigeria prince will automatically be labeled as spam and should be folded in a separate folder, as opposed to other emails that don't have the Nigeria prince as a classifier. And that decision making was the old way of programming about 20 years ago. And the number of rules that you had to keep track of grew in complexity because the new types of new type of scammers and spammers will come up with new ways of writing the same message about, asking you for some information like send me $2,000 and I have a $10 million check coming from the Nigerian prince, or those kind of messages. So if you write decision making if then else statements and try to come up with a decision system that will actually correctly identify whether an incoming mail is spam or not, the complexity of managing such a system over time as new types of spam come in involves you writing and rewriting code. You have to rewrite your algorithm and to account for any changes that happen in the incoming patterns of emails. And these patterns will evolve because people are smart, scammers are also smart, and they will try to bypass your system. And that was one of the reasons why these decision-making systems did not actually fly in the market or in the industry as such. Now, if you today if you look at the way classifiers work, they are not relying on people writing code, but instead they're relying on people using data to have algorithms learn from data and then make a decision based on the incoming data whether a newly arriving email is spam or not. So the approach towards writing code has changed basically dramatically in terms of using algorithms to have a person manage the entire code base to classify a particular incoming correctly. You basically replicate the expert here. So in fact, there used to be a word called replicate the expert. It was called expert systems. This is what I used to work on, but then that domain of knowledge did not fly much. Long ago, this is like 20, 25 years ago, I'm talking about expert systems that did not fly in the industry much. However, the newer systems which involve learning from data have taken off, and you see that already. Now, what I would like to now do is, give me a second. Yeah, there we go. So I want to focus on what we have in the context of this resources available in that the book describes. I'll straight away jump to the beginning of this in terms of understanding the lay of the land, the types of algorithms available, and basically going through the first chapter in the book. Now this book, why is it writing right now? Hold on. So I should use this mouse pad. Okay, yeah. So we got you got the library, the GitHub repository already, which the keyword to search is hands-on-ml. That's what you should remember. Prerequisites will involve some libraries that we have already included in the Docker image, so you don't have to worry about it. Of course, you can read how to build the image itself if you want. And we will now point out to you let's begin to the first chapter. The concepts behind these algorithms. So the thing that we mentioned already, OCR, like I mentioned here, optical character recognition, spam filter that I've briefly discussed. Things like voice search, basically speech recognition, as you know already. This has tremendously and amazingly improved, even so much so that it also understands my accent, which is amazing. I did not expect to have Google and Siri and Cortana and Alexa understand Indian accent, but it does comfortably, no problem, which is nice. But now let us understand, if you really want to get into the types of algorithms available in the industry today, in terms of what types of, how do we classify the algorithms available in terms of buckets of classification, the algorithms themselves, we have a bunch of varieties here. Those varieties are, there are things called supervised learning. There is a thing called unsupervised learning. There is a technique called online learning, which is a misnomer, and a batch learning, which is the opposite of online learning. And I'll explain to you what these things mean. There is instance-based versus model-based learning, and then we will of course apply these techniques to real problems as we go along. Now, a comment here is that if you download the entire Wikipedia, and by the way, the download is available. You can just download the whole Wikipedia. It's like a couple of terabytes, maybe a little bit less or more. That doesn't make your computer smart, just downloading it. It has to function like a smart system. And that's the idea behind it. Now, if you look at the industry today, by the way, this is not a part of the book, but these are my notes in the book. So I have this picture just to illustrate the extent of industry players available out there today, which is how many types of companies are doing a variety of different things in the technology stack, in the enterprise, in building autonomous systems, automatic cars, machines that manufacture, machines that build planes, like in your company, Boeing company, machines that classify goods. So there are a variety of things that are happening in the industry as I'll walk you through examples. But here is a quick overview map, and of course you can download it from this location. And I'll give you a link later on if you're interested. Now, what is machine learning? The core definition according to this book is an older definition here, Arthur Samuel. And the definition is basically a field of study that gives computer the ability to learn without being programmed. So learning from data. You don't have to write code. It will learn from data itself. So it is intrinsically mathematical in nature, and it will learn from the data available as to what the pattern is, and then use that learning to apply to future data elements to decide where it belongs. Classification or decision making or any of those techniques as we go along. There is a slightly more mathematically oriented or engineering oriented definition by this person. And that definition is simply, you can read. I think it's a beautifully written definition. So let's go take a moment to read this. A computer program is set to learn from experience E. So you're basically training it, this experience E, with respect to some task T. So you're doing some task, and there is a performance measure, performance P. If the performance on the task T as measured by P improves with experience. So you're over time increasing your performance of the system. So you have a task T, you're doing it, and you're learning from experience, and your result that you're producing is improving over time as you gain more experience, and the measure of performance is P. Now, by performance, typically most people who deal with computer science tend to use the word performance to indicate speed. Like how quickly can we do it? But that's not the meaning here in performance here. The meaning of word P or performance actually means quality or accuracy. That's what the word performance actually means here, is that the accuracy of your prediction of doing the task T increases over time as you gain more experience. So the word performance actually means quality or accuracy of your work. Doesn't mean how quickly you do it, although that's the traditional meaning of the word performance in today's language, I would say. So this word performance actually means quality. So now, if you have, apply the concept of T and E and P, and the task is, in case of spam filtering, the task T basically means flagging an email as spam or ham. And E is the training data. And this data is continuously provided to the system by people like you and me who are users of email. And I'll show you exactly how you do that, exactly how you train the system. And then P is the actual performance, which is actually how correctly do you classify. Is it correctly classified as spam or ham? And that correctness is the qualitative metric or accuracy metric, which is in this word performance is what it actually means, is how correctly do you have the system correctly classify something as ham or spam on a future data that comes along. Now let's see how a person will train a system. And I am sure you know this, and maybe you have done it already. But what you can do is, let's see if you can find an email. Let's go take a look at this email. So right here, you have this email, which is a critical patch for security vulnerability in recommender X block. So some piece of code, and there is a patch available, and the patch is downloadable. Now I can train the system to incorrectly tell that this is spam. And if I do that, I don't want to do that, by the way, but this is how you can train the system that, any such emails that come from Farhana Sheets, who is an EDX engineer, should be labeled as spam in the future. I do not want to click this, by the way, but just showing you that you can train the system in a wrong way. So I can report spam, and you are then training the Google system, the Gmail system, to look at such emails coming from this person, Farhana, and incorrectly, unfortunately, label it as spam because it is not. And so you can see more such message. I wish I had spam here to actually mark it as spam, so you can see what happens is how you're training a system. But I don't have spam, so I'll wait for it. Spam will arrive, and so when spam arrives, I'll tell you how exactly are we training. Now that training doesn't happen too often. These days, you don't actually go and train the system whether this is ham or spam. At least in case of Google's email, the system of classification works almost perfectly. You don't have to actually go and train the system anymore. And although occasionally you need to, and you can and you should train the system, because the system will learn from your actions of marking something as spam or ham. And that action is the element of training involved in training the algorithm. And that's what you and I and people like us do on a system to train it so that future input, or rather future incoming email, is even better classified as spam or ham, depending on what we have trained the system. So the training data is what we are actually providing online on the fly. And that's where this word comes from, is the online aspect. So you remember we discussed techniques of online learning, right? So here, the word online basically means that people, supervisors, you and me, are going to train the system by labeling as something as spam, or maybe that email is not spam. So you can actually do the other way also. Like, for example, if you have something as spam, which I don't, you could mark a particular email as no, that is not spam. And let's see if I can afford something like that. Yeah, maybe I can show you something like this. So here, this email, you can classify it as spam, for example. So I say report spam. And I just did. I trained the system to mark this one as spam. And I can undo it. So then I can unlearn. I just did that. So it is not spam anymore. Action undone. So I'm happy about that. But that's the element of training that we are looking at. And we are continuously training the system as a supervisor, training the system online. That's the idea behind online learning. The system is learning online as opposed to batch learning. The idea of batch learning is that you provide data to the system, collect it all day long, and overnight, the machine will then start to learn from the data accumulated overnight in a batch that runs over the night. And then next day morning, you have a slightly smarter system. And so it goes offline every night. That is the idea behind batch, is that it is not available all the time online, and it is unable to learn online, and that may be a valid scenario of usage. So certain systems, batch learning is just fine. You don't need to have a system that is continuously learning online all the time, because that may not be applicable for the problem at hand. And so online versus batch, I hope that concept is clear. When you are supervising a system and you're training the system to learn from data that you provided, that you are the supervisor. And the data and the algorithms that are learning from supervised data are called supervised learning. Now I will show you an example of something that is unsupervised learning. And let's see if I can actually pull something up for you. You may have seen it. And by the way, if you have seen such a thing, tell me that you have, which is basically, give me an example of unsupervised learning in action. If you know it, please tell me. I'm going there, by the way.
So you could maybe replay some telemetry that was offline for the algorithm to learn from. That could also be a case of batch, right?
Yeah.
Maybe historical telemetry. Okay.
Correct. So in case of a telemetry example, that's a good example to look at. Let's discuss that briefly. So if you have some kind of telemetry coming up on, let's say you have a Boeing airplane flying. This is the plane. This is my drawing of a plane. So it flies, and it generates data, and then it of course sends the data down to the Earth. And you are collecting that data from a bunch of planes flying around globally. So you have that data about every single thing available that to the company that makes the plane, and you are accumulating that data. And so you can do multiple ways. If you are talking about batch learning, which is the valid usage scenario, nothing wrong with it. But now that you have downloaded this data from multiple planes that is continuously feeding you data as it collects telemetry of a variety of metrics that are in the plane itself, you have a gigantic data store here. And that data is flowing into the system as and when downloads happen. Now, a learning system that you can apply to this data can actually take that from the data source in form of batches and understand and become a little bit smarter overnight, because you will learn and train the system. No, I should not say overnight. Maybe it takes a certain amount of time for the training to finish. And so at the end of training, the system is slightly more smart. And now you deploy this new system in action after the training period is over. And if you're doing it this way, that is when you will call batch learning, because in the training period, the system is less smart because it doesn't have this new data that was injected into the training, because new data came in from a variety of planes flying globally. You now have it. That did not have it yesterday, but now you have it. So your less smart system becomes slightly smarter because you have fresh data in a batch that you feed, and the training will run. And then at the end of the training cycle, maybe it is overnight, maybe it is slightly more, maybe it is a week, who knows how much time it takes, depending on the data, intensity of the data, the quantum of data, and what you are actually training. The system will, from less smart, become slightly more smart because of the new insights available from the data that just arrived in the last batch. And if you extend the idea to online learning, online, where you're receiving input continuously, continuously you see something happen, some new change happen. Like, a user like me is notifying that, hey, this one is spam or ham. That's a notification from a real supervisor. Like this message. Click on it and say spam. That's a message from a supervisor telling you that this email is spam. So that new input will arrive. System has to immediately take that into account and become immediately a little bit more smart based on the input that just arrived on the fly. And the system is not shut down. It is still operating. It was operating before. There is no downtime involved. There is no specifically called out training batch period involved. So the idea behind batch versus online is, think of it as incremental learning. When you're doing it incrementally as new data arrives, you don't shut down your system. You're able to do it on the fly. That's what is called online. Versus when you, in a batch system, you actually shut down your system so that the system can learn. And sometimes it needs to learn not just from the data that just arrived, the new delta, but all the old data also, old plus delta. So both of these things, it is needed. The entirety of data is needed for the entire batch to be run, for the learning to happen. And that requires a lot of time, CPU, effort, and everything. But that's a necessity in some examples, in some cases. So that requires downtime. Your smart system will shut down when the learning is happening and will start again when the learning is finished. And so that's a batch. So it's a periodic cycle that goes down and on and off, on and off. And that's why the word online versus batch comes along. Now, the other idea that I was talking about is the idea of supervised versus unsupervised learning. The idea behind supervised learning is very, very clear. When there is a supervisor, like a human being, telling the system, hey, this is spam. So any such emails in the future, you know what, I don't need to tell you, I don't need to teach you, but you need to become smart and automatically classify it as spam because I just trained you with an example data point, right? So the system has to understand what I'm saying and acknowledge that in form of future actions. So that is a supervisor involved. Now, the question I have is for you, do you know of a machine learning system that you use today that is not supervised? Like not at all. Maybe a tiny little bit. Mostly unsupervised. It just works by itself and becomes smart. Do you know of such a thing? I should say, do you know of an almost unsupervised learning system that you probably use today? So that system that I'm talking about, that at least I know of and I use, you might be using, it's called photos.google.com, or other companies have different methods. And in here, if you look at something like photograph and assistant, maybe, yeah. And so this, I think my library, my photo library, is already trained. So I cannot actually show you a live example, but you may see it if you open up your own Google Photos, if you store photos in Google, and what you will find is that it will show you something that you may be finding it something like this. Let me draw it for you because I'm not able to show you a demo of that.
Oh,
So,
I see. Facebook does a similar thing with our interest, right? Mines our data and finds out.
yes. yes, indeed. And so Facebook does it, Google does it, bunch of other companies do it already today. And what they're doing is, let's go look at the photos example. So Google Photos, if you are new to using Google Photos, you will see something like this. You take a bunch of pictures, these pictures you get and upload it to Google. So photos.google.com, that's where it goes. And once you do that, what you will find is that after some time, Google will suggest to you that, you know what, these guys, this picture and this picture, they look like, they have this person. That person looks like, let's call the person A. This person A appears in this picture as well as in this picture. And this person B appears in all three. And so that's what it will do, is automatically detect faces and club them together as people, person called A, person called B, and it will automatically flag and classify these pictures containing the person. We just label it as A, B, C, D, or this person. Once you go and actually modify the label A with something like, Chris, for example, then the system knows, okay, you call this guy Chris, I know. So now I can detect Chris everywhere across the board in your gigantic collection. So I have like something like, I don't know how many, probably a terabyte of photographs in Google Drive. And so these photos, they are already detecting anytime they find, in my case, Nilesh in any picture, and automatically detecting and putting labels of Nilesh in every picture that has Nilesh in there. And this person B, you can go and say that, you know what, that person B is actually Troy. And so once you label that person as Troy, then it knows that that face or that classifier is Troy, and then it will automatically classify and put bunches, also known as clusters. Clusters of photographs that contain Troy. Clusters of photographs that contain your pet that you might have. And so it will automatically detect and put those pictures together in form of clusters. And all you need to do is go back and label it. Oh, this is my dog, Bingo. Got it. So then Bingo is different from other pets in that collection of pictures that you might have. So that's the idea behind unsupervised, or rather, I should actually call it very minimally supervised system, because it needs to know the name, and it doesn't know by itself. You have to actually tell, hey, that photograph is Nilesh. It doesn't know. It'll just label it as A, B, or person A, person B, person 1, person 2, whatever random name they might come up with. But it knows that there is this person that looks like that, and it appears in P2 and P3. Whereas this other person, I don't know the name, maybe it is Troy, that looks like in P1, P2, P3, all of them. And that's how it will detect and automatically cluster it in your folder. All you need to do is go back and tell, hey, that is Troy, that is Nilesh, and then you're done. And any future uploads that you will do, it automatically detects and puts that classifier and puts that in perspective, and then it will use that information to create scenarios like albums, or maybe create videos of you going somewhere with your friends and family and things like that. And so it is smart enough to, first of all, detect and classify it by itself. And that's the idea behind unsupervised learning. We'll see more examples of that. Now, the next idea here is instance-based versus model-based. That's a thing to understand. Is, first of all, what is an instance and what is a model? So let's go clarify that piece before we talk about those things. So an instance can be something like this picture, P1, that doesn't contain Nilesh and contains Troy. That's an instance. It's a data example. This picture, P3, it contains Nilesh and Troy. That's another instance. So that's what an instance of data basically means. So there is this idea of instance-based learning, where you're learning from instances. And the other idea is model-based learning. So let's understand what is a model. The model is basically, think of it as a mathematical representation of your decision-making system. So you have to have some kind of a mathematical representation. We'll get to that, or come up with a black box function of some sorts that comes out with a value of the answer, which is, hey, that's the answer. So, sorry, cancel. The answer is Y. For a input that you provide, the output will be Y. And so if you can represent it something like this in form of either a black box or a mathematical function, that thing is called model. When you're basically structuring it as a model, you're modeling the data to come up with an output of Y based on the input you provide, X. And that system, when you have a model-based system, is called model-based learning. So that's a simple way of thinking about it, and we'll go into detail as we go along. And let's go further ahead, back here. Okay. So now we'll take an example of the old ways of doing things. Like, I like you to appreciate the complexity that it had in terms of how people created expert systems, which basically was a collection of rules of some sorts. So for example, here, a spam might contain things like the words for you, or credit card, or mortgage, or I block your account, or those kind of, or Nigerian prince. These words or phrases that are typically noticed in spam. So what you would end up doing is write a program that has basically a kind of a collection of very long list of rules that you will keep at your disposal. And in that, what you would do is you will basically write these rules, long list of rules, that you need to grow and maintain, because these things, like, person saying number for you might change and say that, instead of writing, it will write for you like this, as opposed to for you, like that. And so spammers can change things like these. And so if you are writing rules that you are creating to build an expert system that is able to detect whether a particular email contains this pattern, is actually spam or not, that will be an if condition statement. So if this, then not spam, because it is written properly. But if it is this, then it is spam, because it is written kind of spammy. And if it is this, it is also spammy, So then you come up with these method of classification. And so these are rules that, even I used to write like this long time ago, to come up with ideas that will classify, and that becomes really, really hard and really, really complex very, very quickly. Because what you're dealing with is constantly updating your if conditions. If this, then that, if this, then that. And it's very hard to maintain such a code base. And so you will have to learn yourself to understand what is this and what is that and what is that. And then you write rules. And then you evaluate your system and you find that they're not working out. So then you analyze the error. So basically you are working all the time. You learn, you write, you analyze. I mean, come on, don't you have, don't you have life? And so that's the old way of doing things. And so eventually you will get to something that works, and then you will launch the system, but then something changes. And maybe that is, teenagers adopt this short way of writing, the modern teenagers. And they think that this is not spam anymore. So this rule that you had before is not spammy. You may have noticed that younger generation these days writes short for, I don't know what. What's
LOL.
LOL? Yeah, there we go. So LOL, and so or yeah, there are so many of these. I don't write like that, but I understand that it is a proper way of writing for teenagers' perspective. So this is not spam anymore, and so your rules just changed on you, and so now you have to rewrite your system. Oh, that's a big problem. You're writing code all day long and analyzing and studying and learning and rewriting, and that's not fun if you're doing it every single day. So the old way. Now comes the new way. The new way is contrastingly different. What is going on here is that you have data points that you can tell whether this is spam, and this was spam, but it's not spam anymore because the teenagers have evolved and they write it differently, and so that you have to understand emoji these days and all that. So having understood that piece, the idea is that now you have a way to train the system based on data that is labeled. Let's understand the word labeled data. The idea here is let me adjust my pen thickness. There we go. The idea behind this labeled idea is something as simple as this. You have an email, let's call it E1, and that has a label. This email that I have, E1, is good or ham. E2 is spam. E3, ham. Like that. E4, ham. I don't need to go into detail as to why that is ham or spam. I don't need to describe this is good, this is good, this is not good. I don't need to go and describe why it is good or bad. All I need to do is just have a labeled data set. Labeled data. That is what is important. That you have to have a label. And this specifically will be called our training data. You don't need to tell the system why that particular thing is good or bad. Like when you go to Gmail and say, this one is spam. You don't need to tell Google why it is spam. It just is, because that's what you tell. And so the system has to be learning from what you just told them. And so here, I'm just waiting for a spam email to arrive. I'm so anxious about it. I should just stop. Yeah, so spam will arrive eventually. But the idea of training data is what you feed into the system. You don't tell why something is good or bad, because it will change over time. You know that. And so here, what you do is you provide the training data to the algorithm. The data has to be labeled, correctly labeled. This is the most important thing. It has to have labels that are correct. If the label is not correct, it will train bad things, and the machine learning system will learn wrong things, and you don't want that. So your labels have to be correct to begin with. And that is a hard problem to get to this point. Just to get the training data itself is hard, because it may be a daunting challenge to, let's say if you are on the beach and you are trying to find what is called, I don't know how to pronounce it, so I write it down. This thing, it's a type of stone that is shiny, and so you want to go hunt for it. Agate. So you want to find it, and you want to just pick them up because it is kind of nice to have them. Or maybe they have some commercial value and all that. So you come up with a system like a robot that moves on the beach, and it looks for this agate. And so you need to train that robot to detect that, hey, this stone that you're looking at is agate, yes or no. So you want to build a system like that. You look at a stone and tell whether it is yes or no. And so to train a system like that runs around on the beach and looks at all the stones and then tells, hey, this is an agate, that is not. This is an agate, that is not. And when it finds an agate, you should stop and tell the person, the supervisor, hey, I found an agate for you, so go and pick it up. Or maybe the next level of smartness will be that the system will automatically lift it and put it back and move on and accumulate on that agate for you. So to enable building such a system, the very first step that you need to do is to have properly labeled training data, which means you need to have like tons and tons of pictures of things that look like stones that exist in real life, and that you have a label for each picture, whether it is agate or not. And then you use that training system to apply to the machine that you will build. And then it will go with a camera and look at an item, look at a stone, and tell agate or not. And if it says, yeah, agate, it will probably tell you, flag, hey, come, I found an agate for you. And you can go and pick it up. That's the concept. And so this concept, if you are able to collect and generate labeled data, that's the first beginning step. You have to actually go on the beach with a camera and take a bunch of pictures of variety of rocks, stones, or whatever you have, and then decide which of these pictures are actually agate and which others are not. And you cannot have unlabeled data, meaning if you have, say, 100 pictures, each one of them will have to have a yes or no flag for each and every picture. And 100 is a very small number, by the way. You need to have a lot more pictures. The more data you have, the better your system will evolve eventually. That's the beginning point of a learning system, is that you need to have training data. And that is what is a necessary ingredient that goes into training the system. Now, once you have the machine learning system that takes the data as an input, you can then evaluate the solution. And if you like the solution, you can, the difference between this approach versus the previous approach is that here you are writing, you're analyzing, you are learning, you are writing, whereas in this case, the machine learning algorithm will learn from new data that you feed and will continuously adjust its prediction capability, and you will then be able to evaluate your solution and find out whether it is working or not, and then launch your product or launch your service or whatever you have. And it is a whole lot easier to maintain such a system, because all you need to keep doing is to provide new input that is necessary, and the system will automatically learn from what is coming as an input to the system from a training perspective, and is able to predict whether it is this or that, agate or not, spam or ham, or God knows what. That's the concept. Like here, they describe this for you versus for you, and all the new rules keep coming up, but the system will keep learning, because now you will have training data that will provide this new label that LOL, or rather I should say, emails containing LOL will be classified correctly as ham. So then system will learn, this acronym doesn't actually belong in the English traditional language, but now people are telling me that this pattern that may exist in an email, those emails are actually ham. maybe this pattern is not bad anymore. So you learn from it. And then you have the learning will happen because new labeled data arrives and your system gets smarter because of the new data. And you can, of course, adopt in the system by providing it new input and thereby having rec a nice beach as opposed to recognize speech. So you can decide what is the right way to do. And so the idea is to let the algorithm learn from data. Now, when you apply these techniques, you can even, have people learn from the data that is provided to machine learning methods, because it can give people insights into what may be happening from a situation that is otherwise not obvious. And we'll get to some examples like this over the course of the program, as machines can actually help us infer what may be the meaning or what may be the underlying reason or a pattern in a large collection of data, if you have such a data available to you, which most of us do have data these days. And so when you can have machines help us learn the data better, that's very, very important from a insights gathering perspective. And that idea is called data mining, because you're really mining for diamonds of insights in a large collection of data that is otherwise not obvious to us. So this is, in short summary, when the problem itself is fluctuating and data keeps changing on us, like, this new phrases come along, for example, having such systems written by hand when you write rules is not the ideal way. Let the machines learn is a better approach to solving the system or solving the problem. Now, let's get the terminology a little bit here. Online learning basically means learning on the fly, as you already understand now. Trained model. This model is the idea, is where you come up with a mathematical representation or a black box representation of something that will produce an output, ham or spam, a gate or not, this or that, or maybe just a number, 3, for example, depending on what the outcome you want. There are these 3 ways of looking at a potential classification problem, which is one of them. One of them was to decide between binary situations. So you have a yes or no scenario. That's a classifier. Then you have a multiple level classifier. You can have, promo, updates, notifications, like that. So it's a multiple level classification happening, and that's also a classifier problem. When you have a scenario which is not actually a classification scenario, it is instead coming up with something that is a number on a number line, like a value, a real number. That type of problem, which can be either positive or negative, but it's a number. So it is basically coming up with this number or that number. And so when you come up with those values as a result of some machine learning analysis, that type of problems are not classification problems, but they are generally called regression problems. The idea here is that, by the way, I personally don't like this word, because it doesn't convey a meaning, but we are stuck with it. Honestly, this word has been used so much in statistics, and historically it has been like years and years of usage of this word to indicate something that has a number involved. And so that statistical methods of regression have stuck in people's minds so much that they decided to keep that word, even though it doesn't make intuitive sense to me. It might make sense to you, but to me, it doesn't make sense. The word has no meaning to me. It actually has a bad meaning to me, in that it is regressing or going bad, which is not what I want to hear when I'm talking about good things like machine learning. And so Yeah, regression is the opposite of progression in my mind. But that's not the meaning here. The meaning here is simply something that involves a number. So then you can come up with what's the height of this thing at this moment, or what's the length of that thing at that given point in time. So you're coming up with some number. Like, for example, I have this pen in my hand. What's the length of the height of this pen? Maybe it is 6 inches. And so that's the number. So you come up with a value of 6. And that was a regression type situation. So just remember that that's the word people use for indicating real number values for a decision, as opposed to binary classification of yes or no, or multi-level classification, 1, 2, 3, multiple, any number of these can be classified. And there is a third type. The third type is basically giving you a level of probability. Of something. So if you have a threshold of some sorts, where you use that threshold as a hard threshold, and you still have that number line, a real number. When you have, on one hand you have positive, on the other hand you have negative, and then somewhere along the way, at some arbitrary position in the number line, we can come up with something that I would call T, a threshold. Now, if the value that you calculate based on regression comes to this side of the threshold versus that side of the threshold, if that's a hard threshold, if it's a hard threshold, black and white, go this way or that way, none of this, no other situation, either this way or that way. If that's the game you're playing, you're making a decision, which is a classification decision. And you are either this side or on that side, but not both. And in that, what you're really looking at is a binary classifier. But what you're doing essentially is, depending on the number that you get as an output, and you measure it against a threshold, if the number is bigger than threshold, it is 1, or rather yes or no, or whatever the one value of the binary system, and the other side will be the other value. So let's call it 0 and 1 for simplicity. You can call it true or false. It doesn't even matter. Call it yes or no or yes. But that's the binary classification, provided you set a hard threshold. Now, if you don't have a threshold, that's the real number regression problem. If you put a threshold in picture, that becomes a binary classifier, like I mentioned here. And the third variety, which is not so intuitively obvious, which is probabilistic in nature, and that variety involves soft threshold. And that leads to not a yes or no type of answer, but a probabilistic answer with a curve of some sorts. So it's a distribution of probability. So if this threshold is soft, and if it falls this direction, depending on where you lie, maybe it is 20% chance of this way, or I should say 80% chance, or maybe I should rewrite the numbers. So 10, 20, 30% chance and 100% chance over there in the infinity, like that. And same with this other direction. So that's how you should rephrase and understand probabilistic representation of an occurrence of an event. Now, this is very abstract in terms of math, but I'm just wanting to call out these three methods. The classification method, the multi-level classification goes along with it, a real number representation, which is known as regression problem, and there is a probabilistic distribution of an outcome, which is going to predict a chance or the probability of something happening if you have some kind of a soft threshold. And so those are the various ways of us coming up with a variety of examples as we go and study in the program. Now let's go further. We'll now look at supervised versus unsupervised learning, beginning with supervised learning, which is, I think, the most commonly used method. Like supervised learning is traditionally what we see most of the time today is actually this type of learning, supervised. I gave you examples of spam and ham detection, examples of machines learning to recognize speech, examples of machines that are learning to recognize patterns in handwritten patterns and handwriting, like I mentioned, the managed database and postal code, zip code people are writing, and they have taken pictures of that, and then they have trained systems to understand. And in fact, so much so that the postal office system in the US, which is our USPS, they have systems in place that will detect zip code written by people with bad handwriting like I do, and they're able to still correctly classify, and the postal system is able to automatically classify mail in the appropriate bin for the appropriate destination zip code, even though my handwriting sucks. That's a feat of accomplishment, by the way, even for our United States Postal Service. And so that system is actually a supervised learning system, because ton of training data has been provided to the system for it to learn from people's input. Whatever I write here, I write file like this, or I write file like this, or I write file like this. All of these are actually fives, and the labels, or rather labeled data, was provided. This is 5, this is 5, this is 5, this is also 5. And there are cases in which this is also 5. And there are cases where this is also 5. And so it is, I don't think a human being can correctly notify that this number is 5. I mean, I cannot tell. Maybe I look and zoom to see that it is 5, or at least my attempt was to write 5. Maybe I can zoom and see that there is a pattern there. Yeah, kind of, sort of. But that's the idea, that we have collected supervised data and trained our systems to correctly classify even silly handwriting like that. And it is able to tell that this is 5 and not this, which is not 5, definitely not. It's just a horizontal line. So that's the idea behind supervised learning. And let's go see more examples of that. So the idea behind here is that we have labels, yes, no, yes, yes, no. These are the labels, and this is the entirety of the data set that we are providing to the system. So it learns from the data that is provided. And then when you have a new data piece coming in, it can then tell you whether it is yes or no. By the way, this is the ham spam system for email classification. So that's how it is able to do it. And let's actually play examples as we go along. Now here in our example, the idea is looking at a predictor of some sort. So this is talking basically about the regression class of problems, which is you're coming up with a number of some sorts. Like I mentioned here, the idea of regression was basically coming up with some number, 6, for example, on the number line. So you have a number line, and what we want to do now is that we want to come up with a prediction of the price of something. I should not label it here. So it is that. I should say price. What is the price of something? If I feed it an example input, let's say blue book value, for example. So you know what blue book value is. I'm pretty sure blue book value. So this blue book, Kelly Blue Book KBB, what's my car's worth? And so you come up with this, and then come up with an example input for your car, and it will say the mileage is, and say next. So it will then calculate based on your zip code, and then come up with a value. And let's go with standard equipment, and it is, I don't know, this is not the color, but I'll just go with red. And so the value is next. Come on, give me the value. And no, it's not giving. So probably it'll go to give me some value at some point in time, but yeah, I got the value there. So 58,000. That number in that 58,000 number is the KBB value. It is able to come up with a model prediction based on a variety of input that I provided. Let's see what inputs we provided to this guy. So we gave the year, the make, model, the mileage, the color, other options that I did not actually select, but these things were used as input. And it came up with the number 54465 as the price, or rather I should say value of the car. The market value assessed, the trade-in value right there. Private party value is a different number. And so the number private party is 55749, a slightly different number. So just let's go with private party value. Private party value. So let's cancel this out and put in that number 55749. So that is the number that came up based on the input that I provided. Now, how did this system actually come up with that number as a result of estimation of the value of this old car? It is not sold in the market just like exactly like that, so we don't exactly know the price. It is making a prediction of the value of your car based on input that you provide. And so that's the idea here, is that you have data points and then you come up with a new instance. So the input that I provided to this system, KBB system, was the system of me providing a variety of inputs, like in this example, mileage and age and brand. And those are the data points that I provided as input to the system. They're also called features, by the way. So new terminology here, feature. They're called features because we are actually providing features as input so that we can use the word feature, and sometimes people use the word attribute to connotate these things about the input. And then you feed that input and it is able to come up with one number, the value of the car, that number. And the underlying idea is that KBB, which is these guys, have done data collection on a ton of data based on variety of year, make, and model, mileage, color, this and that, and options, and all that, and a zip code, by the way, a key thing I missed, zip code, which location. And so those are features. So which zip code, which color, which mileage, all that. They have done in this work already, and based on that data that they have it in the marketplace, what they have done in building this system on a up to this point is that they had fed the system training data that contained these data points for the variety of features with a label that correctly valued and assessed the value of every data point in the training data set, with a label that is a value element of every car in the database that they had up to this point. And they keep improving the database based on what they observe as new data points, as new training data, and that's how the system is evolving. And it's kind of very, very decent in terms of its prediction of a value of a car. And I think this number is probably right. If I attempt to sell this car on Craigslist, that's the number I would probably sell it for, is my estimation. So it's a very reasonably functional system that actually does a decent job in coming up with predictions for valuation on a number line, which is a regression problem in Kelly's blue book, like we saw here. So that's the valuation. Next one, there are a variety of algorithms. And what I would like to say, one thing, those of you who are new to this idea of machine learning and artificial intelligence, is that I like to say it this way, is that there are really complex sounding words, and they sometimes don't make logical sense to common English reader. So it may not have any meaning, like the word regression. To me, regression is the opposite of progression, but that's not the meaning. So support vector machines, they can look daunting to some people, depending on decision trees and random forests. So what I'm really trying to say is that all these fancy names that you will encounter, and you will see a lot of these things as we go along studying a variety of things. One thing to remember: don't read too much into the names, because they don't really matter. It doesn't matter how complex and fancy neural network sounds, or deep learning is not deep. It has nothing to do with deepness. To me, it's just a name. So just discount the aura, or the scare factor associated with complex sounding words, and you will be better off. That's what I would like to say. They might sound complex, but they are not. They're not complex at all. As long as you treat them as a black box, it is not complex. It will work for you. It will get you the results you want without even understanding what is inside the black box, honestly. But that's not the goal. The goal is to understand. And yes, we'll get to that point. But what I want to say is, as you begin learning these algorithms, you don't have to worry about how complex they can be under the hood, because they are complex and they might sound daunting, but don't scare yourself. They're easy to use. You can put them to function for you effortlessly, and you will see as we go run live examples. Don't get scared of big words, big sounding words like neural networks and neurons and random forests and trees and ensemble, and goes on. And the book and the whole topic and the whole mathematical field is full of such complex sounding. And honestly, I used to get scared of these words when I was learning a long time ago. But there's nothing to get scared of. That's what I want to say. And what you're reading right here in the short list is a list of some of the most important supervised learning algorithms that are a part of the scikit-learn library. So scikit, come on, 10. There we go. Scikit-learn, that library has included support for almost all of these guys. And this number 2, TensorFlow focuses more on this segment. TensorFlow, by the way, is available on the smallest devices all the way to the biggest gigantic devices. And one of the beautiful videos that I think I saw, and I should just see if I can show it to you quickly. It's more like a picture than a video. So, but let me get to that. See if I can find it quickly. It is on desktop. Desktop has a video of TensorFlow processor, TPU. It's a very small TPU that has recently, I saw it. And so if you search for, yeah, there we go. So this is a small video. It's like 14 seconds. But what you're looking at is a TPU. Let's go pause it right there. So this unit is almost like, as you can see from the coin size, this is a TPU unit. The size of the 25 cents or $0.25, as you see, is the example put in just to help you understand the size of this TPU. This is a dedicated processor that runs TensorFlow, and it is available on platforms like, what is it called? Raspberry Pi. Yeah, go ahead, Chris. Chris, you had a question? Probably not. So that's what I wanted to point out to you, is that these things are available on the cloud. In almost every big major cloud support provider, you will have TPUs. If you go look at console.cloud.google.com, there's a TPU option. In Amazon, you can find TPUs. If you go and say create compute engine TPUs right there, and you can basically create a TPU node, TensorFlow processing unit node, dedicated FPGA architecture ready for you to consume and run TensorFlow algorithms on the fly as you need to, and shut them off when you're done using them. And that is available in all the big clouds. So we have 3 of them, big ones: Amazon, Google, and Microsoft. All of them support these things for you to run TensorFlow processing, as well as understanding and using this Kit library. This library is actually a comprehensive library containing almost all the algorithms implemented for us. And so we'll use this and then switch to TensorFlow for a specific deep learning perspective. So these are the supervised learning algorithm names, and we'll go through each one of them to help us understand what do they actually do for us, and then use them in the context of supervised learning. Now comes unsupervised examples. We already mentioned this of an example of a system that tries to learn on its own without a teacher, without a supervisor, and is able to correctly bucketize or create clusters around whatever you provide. So you send a bunch of pictures to some kind of a photo library, like Google Photos, for example. It will automatically create clusters of people that are together, or the photographs containing the same person, or some other types, pictures in one location, or things of that nature. It will basically create a cluster of these photos versus those photos are somehow separate. So these photographs are somehow separate from these, and so it has already placed them separately. It is up to you to label them further if you want. But this is basically based on an unlabeled data that you just throw at it, and the system is able to then learn from what it finds on its own without involving any human being in providing any kind of training whatsoever. And here are some unsupervised learning algorithms, which are k-means, clustering, hierarchical cluster analysis, and all these names, as you will see. Some of the simple ones that you may have heard of put in place are principal component analysis and the a priori algorithm, which is a statistical algorithm to understand association rule. You may have seen this implemented in shopping carts. So you see what is known as people who buy this also bought that. That recommendation system is basically based on this algorithm. It is the association rule learning, which is, people tend to associate hamburger with, buns, and they will buy these things together, obviously, because you want to eat them together. And marketers will introduce some complexity in there deliberately to have, I don't eat hamburgers, so correct me if I'm wrong, but buns come in 6-pack and burgers are in 8-pack or something like that. Some deliberate mismatch they have done. I don't know what is what, but you can tell me and correct me if I'm getting it right. You know this, you know what I'm talking about, right? Bun versus, or something like that. So one comes in 8-pack, the other comes in 6-packs. What is what? Do you know?
I don't know, but I know that they're mismatched.
Okay, but these are marketers introducing non-linearity primarily to make you buy more stuff. But the idea is that people who buy this and that, they buy it together, and that association is detected in case of, say, for example, Amazon.com. And you will find those live examples when you go and buy something. So let me just see if I have shopping cart, and let's go to see. So people who buy this book, let's see, what do they have? People who buy this book also buy these books. That association, customer who viewed this also viewed that item. Customers who also bought this item also bought these items. That's the association that is happening at the back when this algorithm is running. And that you will see when you apply those techniques as we go along. So unsupervised learning, we already mentioned. Here is an example of another unsupervised learning when the machine is fed with a bunch of pictures containing cat and automobile and truck and frog and this and that. So what it is going to come up with is the TSNE visualization technique, and it will automatically place these items on a pictorial graph like this. And as you will see, certain characteristics of deer and horse, they are deliberately placed closer to each other as compared to horse and bird. They are kind of far away from each other. So it's already understanding the association between a deer and a horse. Both have 4 feet. Birds don't have visible feet. They have wings and things like that. And truck and automobile and airplane are kind of different from horse, so that's completely separate separately placed horse and deer and dog here are kind of in the same region. Of course, they're different in size, and so cats are in a different segment. So, by the way, these are after the fact labeling that the machine was able to automatically cluster and create an unsupervised example. Now we talk about these things that I mentioned as features. And features is something that as a new program developer or a new machine learning practitioner, some people like you and me have to come up with these things that are relevant that will be called features. And we have to come up with these metrics as input that we need to provide so that the system can then use that input to correctly train a system. And those things is something that takes a lot of time to come up with the right set of features and then make sure that we are able to use that data that we provide to apply that to an algorithm and then come up with a decision that the machine will help us and basically do our job much more efficiently. Another such clustering example will also help us analyze what is known as anomaly. And that is a case in example that also comes in very, very useful. And that is something that an anomaly will look something like an outlier. An outlier is something that doesn't belong in the main set of data points. So you have a bunch of data points. For example, I have a credit card, and I have credit card has transactions. And so I have this credit card, it has transaction with this dollar amount, another transaction, that dollar amount. But what is also there in the credit card is the location of purchase. And so you may have noticed this as you go and shop online, or maybe when you travel abroad or other places that you usually don't, is that this information is also tagged associated with every transaction that you make the transaction at. So either it is online transaction with an IP address, or if it is actually you traveling to Thailand and you transacting it in a swipe transaction on the credit card, like that, you will have this location information also available, the dollar amount, the date and time, and the item being purchased, the merchant name, that data point is available. Now, if you have such data already on your credit account, and the bank has data about these kind of transactions across the board, across their countries of operation, wherever they operate. And so the bank already has a ton of data that they know that such and such transaction is valid or not. Is it a valid transaction or not? And if it is found to be invalid transaction, the bank needs to be smart enough to detect that this transaction that's happening in Thailand on a swipe, when this guy, Nilesh, doesn't usually visit Thailand, and he did not even tell us before visiting Thailand that he is visiting Thailand. So this transaction that happens seems to happen in Thailand when Nilesh is most of the time in the US and almost in Seattle area and doesn't even go out of Sammamish. Maybe that guy, why his card is being used in Thailand? Suspicion. Now that suspicion needs to occur automatically, and that transaction should be flagged by itself as an invalid transaction and should be blocked. Or if not blocked, at least notify Nilesh that, hey, this transaction is going to happen. So either you call us or you pop up online if it's an online transaction. Like, for example, the other day I purchased from this called JD.com, like this JD. I'm not sure if you know this or not, but this is a Chinese website. It's a actually the name is Joy Buy. It's a Chinese website, and the name is kind of unfamiliar to US people, but it's a well-known company called JD, and it's on NASDAQ, and they have things, and I bought something. So when I buy this, and I'm living in Seattle, and I go to this Chinese website, and I process the transaction gets flagged. and it was blocked. But the good thing is that the bank is smart enough to actually pop up right in front of me saying that something that I find it unusual. So they create a separate pop-up and let me verify my identity, and then the transaction goes through, and then I got the item that I wanted to buy from this site. So that detection of anomaly happened, and it correctly signaled me as a user who apparently may be purchasing this item. For example, if I'm buying this item and I say add to cart and buy it now, that's the idea, is that it will then ask me for a credit card. It detect anomaly. If it does, it would, because the transaction seems to process from Hong Kong and I am here in the US. So that's not where I usually visit. These websites I don't usually go to, but then our bank is smart enough to detect an anomaly and not actually block, because I'm a genuine user, genuinely trying to purchase from this website. So it lets me buy these things. And that's the goal of detecting anomaly and then correctly making a decision whether the user should be blocked or not. And that anomaly detection is possible through the same idea that we mentioned is also unsupervised. So the system is able to detect anomaly and is able to capture that, and then you have even smarter systems to create a pop-up, let the genuine user validate, authenticate, and then allow the purchase. And otherwise, if the user is not able to genuinely validate themselves, then the credit card transaction should be declined and the transaction should not fly. If I am visiting Thailand, that the bank should know, because they should ask me, and if they don't, then they will probably taking some risk in terms of approving that swipe transaction. And that's why the number of items that banks need to put in place to reduce the risk of such transactions happening when I travel without notification to Thailand, for example, that can be reduced by using a certificate on a chip. You may have noticed that these days credit cards have a SIM card like chip in there, which stores a private certificate right on the chip. And so you have to actually insert the card in a chip reader, which reads your certificate from the chip. And so it is kind of a method of authentication or verification of identity, for example. And that is a slightly improved system, which has reduced the chance of a credit card fraud in the example that I just described to you. I already mentioned market basket analysis, which is, if you, the example they're providing here is barbecue sauce and potato chips. People who buy barbecue sauce and potato chips also tend to buy steak. Now that information, I have no idea. I don't eat steak and I don't eat the barbecue flavor much. But what I know from now, because the system can actually detect this from a priori probability, also applied in the context of association rule, is the idea called market basket analysis. Even if I am not super familiar with the fact that people seem to be buying steak when they buy barbecue sauce and potato chips, that system can actually teach me as a store owner to put these things together. And even if I'm clueless as to what steak is or what barbecue is, which I was, by the way, 20 years ago, I had no idea what barbecue is and what steak was. I knew steak of something that you dig in the ground and mount a pole or tent or something like that. That's what I knew as a steak. But yeah, so people who don't know, or people who don't have that insight from the system, can actually tell you that people who buy A and B may also buy C. So if you're a physical store, you can probably place them together in the same shelf. If you're an online store, you can probably suggest that people who buy this also buy that. So then you can just have both of them added to the cart. And so that technique is not intuitive enough for most scenarios where the number of items being sold on large websites can be millions of items sometimes. Like Amazon sells probably more than 1 million items. So it is impossible, humanly impossible, for any person to actually identify which products are being sold with the other products. And that's where this kind of an association rule, also known as market basket analysis, can come in handy to give insights to Amazon so that they can actually place links of items together, as opposed to placing two items together on the same shelf in Safeway or Costco. Costco doesn't do these things. They don't need to. They're a different game. They just sell volume. But so semi-supervised algorithm, the one I was mentioning about Google Photos, is the idea where you have a photo, a person A shows up in photo number 1, 5, and 11, for example. I think I already mentioned. So here is Nilesh. So we just have to go and label, this is Nilesh. Then it knows that, okay, all these guys are Nilesh. So that's good. And then you have the idea of classification of a cluster, and the system then knows how Nilesh looks like, and then it can then deal with it by itself. Now, here are more complex sounding names: deep belief networks, restricted Boltzmann machines, things like that. So don't get scared. They're just names of algorithms. You will see them in implementation, in action. And if you want to go further and understand the theoretical aspects, I'll give you some reading material, and you can go further. If you're interested in a particular one, you have to go really deep and really down in the math and statistics and understand the concepts before you even but getting to use it is fairly easy, as you will see as we'll do it. So using that is one game, but actually understanding the algorithm and going down to research whether that algorithm is done or doing its job correctly or not will make you a machine learning researcher. And that is not the goal of this program, by the way. Just want you to know that we are not trying to make you or develop you into machine learning and artificial intelligence researchers. Our focus is to help us become better practitioners of what is available out there in the industry, in the ecosystem, on the open source libraries that already exist. And they are doing a fantastic job, no doubt about it. Beautifully run, beautifully written code that works almost every single time that we try. In certain cases, you will have edge cases when you need to study and research as to what may be a better way of doing certain things. And that is a research cutting edge field that is continuously evolving. And you will see, next time we run the bootcamp, we will have something new pop up. That happens all the time in every field of knowledge. So these things are useful. They are applicable. We can become good practitioners using these things, but we will definitely not become researchers unless we actually go deeper in the math. Just want you to be aware of that fact, that this bootcamp is not going to make you a researcher. I think that is clear. I hope that is clear. So let's go further. There is one more type of learning, and that is reinforcement learning. And it is actually intuitively simple to me, and I'll explain to you what it actually means when somebody says that method of learning is intuitive, or rather I should say reinforcement learning. The learning goes like this. Imagine you have a small child who is sitting on the ground, and there is a cup right there. And that cup is probably, it has some vapors coming out of it. It has some liquid, probably hot milk. And so the child goes and touches it. The moment it touches, the child detects a reaction, which is, ouch, it is too hot. So then the child walks away or puts his hand away from the object, which is apparently the hot object. The child has no clue whether it's a hot thing or a cold thing. So the child just approaches that cup. It's hot milk there. And so the child is getting a punishment in terms of ouch. And the next time the child again approaches that object, the hot milk cup, and the child notices that there is some vapor coming out. In that case, the child will again touch it and again get that shock and get, ouch, and walk, take the hand away from the cup, the hot cup. And as a consequence, what is happening is the child is getting punished, if you will. A punishment is just my phrase of saying it, is that it is feeling the heat from the cup and it is getting punished. And thereby, the child is learning in their mind, and that learning is getting reinforced that if you see something that is like a cup and you have some vapor coming out of it, that means that this thing should not be touched. and that's the learning. So you are getting a punishment. Sometimes you have a reward of it, like you have a cup which has something sweet in there, or maybe some orange juice right there, and maybe sweet something. The child looks at the cup, and he or she wants to grab that cup, and the cup is not hot or warm, not too hot, so it's able to hold it, and then takes it and tries to drink and enjoys it. That's a reward. So this reward versus punishment, that game that we are playing, is actually reinforcing the child's behavior. And so it notices that the cup is not fuming in terms of vapors coming out. Maybe it is something interesting. So he or she will try to approach it and hold the cup in the hand, and thereby potentially getting a reward. And then every time it looks at something interesting or sweet, it'll go grab it and drink and have the reward, and then it'll learn. And that's the kind of system that we are looking at, which will be known as reinforcement learning, because it operates just like I described to you. The system observes and it selects and takes an action of some sorts according to a policy that you set. And that's the policy that you need to act on. And so it detects something, observes something, and it finds that it is something that it needs to do, so it does it. And then as a consequence of doing it, it gets a reward or a punishment. And based on that reward or punishment, it will adjust the policy to do this versus that and maximize the reward the system will get. I'll see if I can find a live example of something that will reinforce the idea of reinforcement learning. I think it's called cart pole. Let's see if it comes up with, yeah, this is it. So let's see if I can identify the right video. Yeah, I think this one is a good one. So it's a 2-minute video. Let's see it, and you will see what a cart pole reinforcement learning is in terms of. Let's go straight to it. So here's the machine, and let me just mute it. So the machine is, after so many tries, is trying to learn how to balance that pole. You will see that the machine, the person is deliberately bringing the pole back up. After 52 episodes of performance, the system is trying to balance the rod or the pole and try to keep it straight up in the air. And after so many attempts of learning, it is still failing. And you will see as the person tries and trains the system over and over and over again, at one point, it is able to quite a bit balance. After 102 episodes of training, let's see, even better. And effectively, I think if you just scroll ahead a little bit, you will find that the system is able to balance quite a bit. And the guy pushed. And after 228 episodes, the system is able to comfortably understand how much of a force even he tried to disturb it and it did not disturb. And it is able to balance the pole comfortably. And that is going on because of reinforcement learning, which happened on the fly. And so here you just let go of the pole and the system is able to correctly balance it based on the corrective action the system needs to take, even if the person is deliberately pushing it to some extent, not too much, but a little bit. And system is able to tolerate that. And after the system was stable, it was able to maintain. And this is just unidirectional, by the way. What you saw was unidirectional reinforcement of a cart pole, when there is this pole being balanced on a single x-axis. Think of it as an x-axis balancing a pole. That's pretty much what it was. But it was a successful experiment when the machine was able to balance this thing on a unidirectional one axis. And it was able to do that through reinforcement learning, because the policy was to balance the pole. And so if you have gravitational force this way, then the pole, the bottom will move that direction to adjust that. If you have the gravity pushing it this way, then you move it, the machine this way. And this is a motor at the bottom, which is a step motor. Basically, it's a digital stepping motor that actually detects how much motion, how speed, what velocity, what acceleration it needs to provide to get the pole to balance correctly. And it is adjusting its own policy, updating the policy to maximize the reward of a cart pole balancing act. It gets a reward when the pole stays straight. It gets a penalty when the machine is unable to maintain the pole straight. So if it tends to fall this way, it corrects the position so that it is able to avoid the fall, and it automatically updating its policy on the fly after so many iterations. And I think what you saw was like 228 or so iterations. It was able to somehow understand and reinforce its own policy correctly based on rewards and punishments that is being perceived, to come up with the right position, velocity, acceleration of the underlying step motor. And to basically balance the pole on that one direction or one axis. Another example of a agent looking at hot versus cold items, and you get an ouch right there, and you get, next time avoid it. Don't touch the hot thing. Maybe go to the cold thing. You might not get punished, or maybe you get a benefit of some sort. So depending on what the reward and punishment structure is to modify the policy. And that's the idea. Now, what has happened in the past, as late as 2 years, 3 years ago, was this thing called a company called DeepMind. I think they got acquired. DeepMind. I think Google bought them. So there was a company called DeepMind which was able to. The underlying story was like this. It was given the game of Go, and it was told how to play that game. And what the machines did was that they created multiple games of the game Go and had multiple processes. So process number 1, process number 2 play with against each other. This game of Go hundreds of billions of times, and thereby learning which moves are good, which moves are bad, and were able to reinforcement learn by itself, by simply analyzing millions of games that the machine played with itself. And then they had a real life match with the world champion. And this guy, who was the world champion of the game of Go, got defeated. And that was the news, I think, in March 2016, when the machine was purely learning on games that it played with itself, and based on a set of policy as to how to play, what to do, what not to do, what moves you make, what moves you don't make. And then based on what it learned from learning by just sheer amount of number of plays of games, that it was able to beat the world champion. That was something that is amazing in terms of just thinking about it. Is how can you have a machine learn by itself based on reinforcement of behaviors, and put that into practice. Let's now look at batch versus online learning. I think we already briefly discussed this. Batch is not incremental, and online learning learns on the increment as new data comes in. And so as you know, when you have resource constraint, you may not be able to run the entire set of data and entire training all by itself. Like I mentioned here, if you have a batch system, and the batch system might require your entirety of data, plus any new data that you might have, incremental data, and that entirety needs to be run as a training input in a batch mode. That will require a lot of time and resources. So it's basically expensive. And so if that is the case, you may not want to use that kind of a system if it becomes really, really expensive. And in that case, you have to maybe switch over to another method in which it is able to learn incrementally. In that, what you do is you have the entire data and you learn from it. And then you get new data, incremental data, and you just use the incremental data on the fly and iterate on a newer version based on as soon as the new data arrives, you get a new system and use that system to basically, then you disable this one and start using this one as soon as the new data arrives, and that one becomes active because you now have new data added on to the existing system, which then becomes the new system that you have because it learned incrementally. And that becomes a efficient model of usage that is mostly the case of most of the online learning systems like SPAM, for example, that you saw. Or what we are doing essentially here is you get new data on the fly, and you use that data to learn and run on the fly, and you don't have to use the entire data set that you had to begin with. And you are able to basically, without spending too much money, you are able to learn on the fly as it goes along. And what also is a case in which this model is kind of useful is a scenario when you have systems that are small, that cannot even fit in what you would expect. For example, this new thing that has come up, which is, new phones from Apple, for example. They are small in the size, in the amount of memory that they have. Or you have Raspberry Pi units that you can program yourself, and they don't have enough resources to begin with. So doing this incremental method of learning is a attractive model because there are certain cases in which the data can be really large and you cannot even fit the entire data on a Raspberry Pi or a small unit. In that case, you have to have a system in which the system itself needs to be able to learn from scarcity of resources. And if you're not able to fit the entirety of your data set on the main memory of the system, if it cannot fit into your main memory of your system that you're using, that method of learning is called out-of-core learning. It basically means you're using extra storage of some sort somewhere else. So basically, that's what you need to remember. This is not very commonly used phrase. Out of core, if it cannot fit into main memory, that's what it's called. But these days you can have algorithms written efficiently that doesn't matter whether you store it in memory or disk. It'll automatically pick up the right amount and handle it for you. So that is not commonly used phrase, but it's something that I want you to know is the word people use, out of core learning, as a method when you cannot fit the whole data set in your main system's memory. Let's see. Now, another thing that we need to understand is the rate of learning. So that's another phrase I want you to be aware of, is the idea of rate of learning, or rather learning rate. So learning rate is something that how quickly or how fast can you have a system learn, and you rapidly are able to respond to a new data point that you receive in terms of labeled data. So the idea is that if you have a system to deal with spam, the idea is to flag only the latest kind of spam. So the latest kind says LOL, not spam. That's the latest kind. The older kinds, you can ignore them. So the idea is to have a system that is able to rapidly forget old data and learn from new data. And so if you actually have a very fast learning rate, your system will correctly mark emails containing LOL as not spam, but in the consequence, it might tend to forget some of the older types of spam, and so that spam might seek in. And so that is a challenge. Somehow you have to maintain and understand that the speed at which you're at the rate at which you're learning can make your system faster, but at the same time, it might forget to correctly classify historical or older type data that is not so prevalent, and that is a challenge. So on the other hand, if you have a system that is slow in its rate of learning, it will learn slowly, which means it will be less sensitive to noise. So tomorrow, for example, people start to write LOL lowercase as opposed to lowercase LOL or uppercase LOL, and maybe there's a meaning difference in the two, and the system is able to handle that because it is going to ignore these short-term transients, which is, you can call it as noise in the input that comes up as something that can be ignored, whether it is LOL or LOL, both are okay. And sometimes you can have data that indicates otherwise, but if your system is a slightly slower learner, that's maybe a more reasonable scenario in certain applications. Again, of course, it depends on the system's actual application as to what you want. Now, the trick is that you want to really have a learning rate that is optimal, because if you have a fast learning rate versus slower learning rate, you have the problem of noise trickling through as a actual input and actually mutilate or make your system go bad. If you have noisy data or wrong data that you feed, and you have a fast learning system and you feed it somehow incorrect data, then the system will end up quickly learning wrong things. It will learn wrong things and start to do wrong things very, very quickly. And that is going to be a problem. So if that happens in real life, a good way to handle this is to think about, first of all, lowering the rate of learning. That's a good way to lower the rate of learning. That's a good way to think about. The other approach to solving this problem immediately, when you have some incorrect input that somehow reaches your system, the system is a fast learner, so it basically learns the bad data and starts to do wrong things. So in that case, what you need to really do in practice is to make sure that you keep a snapshot of your system every so often. Probably a nightly snapshot is a good one. Every night, take a snapshot of your system, and if you notice that you have somehow seen incorrect data flowing into the system that has actually made the system go a little bit dumb, and in that scenario, what you need to do is basically revert last known good state. But for that to happen, and you have a fast learning system, and you apparently detect that something has been incorrectly trained, you got bad data in the training set, the system quickly picked up all this junk and is able to do incorrect or bad things, and you detect that as a problem. And then what you have is that you have been taking snapshots of the entire system. So you need to then quickly revert back to the last known good state, and you're back in business, because what you're effectively doing is that you got rid of all the bad effect of the incorrect data that was accidentally or erroneously input into the system, and the system unfortunately picked up on the wrong input and became bad for the short period of time, but you reverted, which is a good thing. And then you can, of course, go back and do a deep dive as to what caused the input to go wrong and all that good stuff. And a live example of this would be that I actually go back to Gmail and send an incorrect data, for example. And so say I have this spam, no spam, trash, maybe. There should be some spam here. Okay, maybe not. Actually, I don't have, crazy that I don't have any spam. No, oh, not even my trash. So let's say, these are reports that I receive. So some security outputs that I receive occasionally, and these are sent by me to me. So if I accidentally mark them as spam, for example, right there, and when I click this, I am creating wrong input. If I click this spam button right now, and if I do that, or rather, a number of users do this kind of behavior by mistake, that data gets fed into the system, and the system is a fast learner, so it starts to mark this good email as spam. But this actually is coming from one of my systems. So it's the security check happens every so often. And so that is a good email I need to receive, and I do receive, but if I incorrectly flag and send the wrong input, it will learn the wrong things, and then we are screwed. there is no way to revert back unless somebody is preserving the state. And that is important to remember, is that you need to do this thing, snapshots. Every single time you're running a system in production, make snapshots. A better way to do these things is to slightly lower the learning rate so you have time to react, and these transient inputs may not have enough bad impact to begin with. That's another approach to handling the same problem. Now, in terms of course, the performance, meaning the quality of the system declines, you switch off your learning or revert to a last known good snapshot. Now, we should discuss this idea of instance-based learning and model-based learning. I think I already mentioned this briefly, but I'll go slightly more elaborate in terms of what we have when we say instance-based learning. Is to basically, this is the most trivial learning. It's like learning from rote, like you memorize the whole thing. And that is a problem in that, first of all, you need to memorize, which is a problem to begin with. And what you do is, if you have like a bunch of emails that are labeled as spam, so this is your training set and the training data set, and you have email, spam, label, and this is data and the label. So we have that and a lot of these things. Now, what will happen is, in the instance-based learning system, all these data points, the system will just learn by rote. Is it this rote? Is it how you write it? I think so. Yeah, learn by repetition, memorizing the whole thing. Memorize the whole thing. And by doing that, what is going to happen is, if an email that comes that is exactly identical, it will then, since it's learning by rote and by memory, if it is exactly identical, then it will get classified as it was spam in its memory, in the input. So then the output will also, another email that is identical will also be flagged as spam. But what if that is not exactly identical, but similar? If it is similar, that will not work. That will not actually produce the correct output, even though it should be spam, but it is not identical. It is kind of sort of similar. It should be classified as spam, but it doesn't get classified as spam. It goes as ham, which is a problem. And that is the problem of instance-based learning, which is, it just memorizes simply. And that's what, if you read here, if you were to create a spam filter, it will just flag all the emails that are identical to the system. And it's not the best solution. The better solution, by looking at or is to use some concept of similarity to come up with a method of generalization of an identity. So if you have this method that you have remembered already, you need to be able to have a system that also identifies similar emails and is able to correctly label those as also spam as opposed to not. That's the instance-based learning method. And I personally prefer methods that are model-based, which we'll talk about next soon, which is, here what we are doing is, in instance-based learning, it is looking at these instances, and it knows that there are some things that are called squares and the other things that are called rectangles. So whatever the new things that are going to come up, you can then correctly label them depending on what the pattern was, because you already know it's a square, not a triangle, not a square, or square or not a triangle, like that. Whereas in case of a model-based learning, you are coming up with some idea of, like in this case, this line that we are drawing here, this line. That line is able to segregate the squares from the triangles in some concept. And so this representation of a graph that draws this line, almost artificially drawn, of a line that separates the squares from the triangles, is the idea of a mathematical model. You can probably represent this in some form of a function, whether it's a black box that you treat like a function that goes like this, or you can then come up with a multi-order polynomial that fits this curve pattern. or maybe it's not possible to fit a curve pattern. Maybe it's a broken multilinear pattern or any other mathematical representation, or not mathematical, but still a representation of some sorts that is able to classify and segregate. And that representation itself will be considered a model to make the decision whether an item is a triangle or a square, or whether it fits in that group or that group, this group or that group. And that's where you come up with this idea of a model. So what we want to now do is to to identify a model in which we'll actually use some real data. So here's the data coming up in the example, and the idea is to find out if money makes people happy. That's the idea. Does money make people happy? That's the question. And we want to find that out based on the numbers that we have from this thing called Better Life Index. That data is available from OECD website, which has some statistics available. And also we have another data point available from IMF website, which also has some data points about GDP per capita. So there are two data sources from two different places. And so from these two places, what we get is this data set, which is these countries: Hungary, Korea, France, Australia, and United States. They have the GDP data points mentioned out here, and also the life satisfaction. This life satisfaction rating comes from the Better Life Index from this agency's website. So what they have done in this sheet is that they have come up with the numbers that show satisfaction, and also come up with how much money per capita does the country make, the GDP, gross domestic product. And they plot this on this sheet of paper. And now what you see is that there are these countries that are labeled in red are Hungary, Korea, Australia, France, and US. Now, is there a trend? Does it make some kind of a sense that if you identify these red lines or other red dots and try to draw a trend line of some sort, does it mean that more money per capita means more satisfaction? Is it true? Is it generally true? Can we absolutely say that? Probably not, but kind of sort of yes. But this point, is higher in satisfaction with low number of money, whereas US is lower in satisfaction with higher number of money. So that kind of defeats the point. So you cannot generally say that that is the case, but there is a trend. That's what you can see from the data that we saw. The life satisfaction, Australia, less money, more satisfaction compared to US right here. That's the reason why you notice what you do. Now this, what I just drew in terms of a line that I try to fit, is a well-known method. It's called line fitting, and this is implemented in Excel. Excel can also do curve fitting for you. A bunch of other tools already do that, and we will be using Python, by the way, to do these things. We'll be using NumPy, all the built-in libraries that already are there with scikit-learn, and actually identify and work through our problems in that notebook that I mentioned, which we will set up soon. And if you have a system running Docker, it's like a 2-minute exercise, and you will have system up and running. But if you don't have Docker, of course, so before the next session starts, which is I think Thursday, what I would like you to do is set up Docker. And I'll guide you through how to set up Docker if you're not familiar with it. I'll actually show you that piece. It is kind of not tricky on Windows, and it's super easy on Mac and Linux. So many of you probably have already set up Docker, so I'm not worried about that. Having said, let's go further. So what we are trying to do is that line that I just drew on this sheet, which I should erase, but that line is what we are trying to come up with mathematically. And because that is going to be a simple linear model to make a prediction for a new country, for example, and we'll come up with a country that will have data for other things, but no data for life satisfaction. And we'll try to make a prediction based on that country. So we'll use the country called Cyprus. And so we'll have to find out whether Cypriots, the people from Cyprus, are they happy, and how much is the life satisfaction index or happiness index for that country for which we don't have data. That's the kind of prediction this simple linear mathematical model will attempt to create. And in simplicity, what a line is basically, so think of it as a line, and you have a slope, and this is simple math. The slope is, say, m, and this is the offset b, and this is your x-axis, this is your y-axis. So if you already know the equation of this straight line that I have, the sloping line, it is y equals b plus mx. If that's the representation in your country or your style, other countries will represent as mx plus b, other countries will call it mx plus c. And in this example in the book, they are using equation like life satisfaction equals theta 0 plus theta 1 times GDP per capita. So the GDP per capita is your X value. Life satisfaction is your Y value. Theta 0 is the B value I mentioned. Here is the offset. And theta 1 is the slope, the M value. So that's theta 0 is B. And so that's what we are really dealing with. And you probably, in high school math, you've seen it. Y equals mx plus b. It's very common. That's what we are really talking about right here. Right here. Y equals mx plus b is, I think that's the US convention of writing in high school math. I did not go to high school in this country, so that's why I'm kind of confused as to what do you use in this country. But other countries will probably understand. So I hope they understand. Having said, it's a simple linear model. So that's what you mean when you say coming up with a model. Is what we are really doing is coming up with this math, an equation, for example. And this being a straight line, it's a linear model. And that's why the linear word comes from. It's a straight line, two parameters, theta 0 and theta 1. And these are the convention that this book uses. But you can use any convention you like. And of course, it's just a convention. So if you now, get what I would say, the model to tweak a little bit in terms of the values of theta 1 and theta 0. If you tweak them, you can get different types of lines. For example, if you have theta 0 as 0, meaning the offset that we have here, the b, if that is 0, then you have the red line there. Do you see the red line? That one? That's the theta 0 being 0 right there. And it crosses the y-axis crosses just at the 0 point. The line cuts at the 0 offset. But that is not a good indicator of your estimation of life satisfaction based on data points available to us. So what that machine learning algorithm in its simplest form or simplest fashion is going to come up with the values of theta 0 and theta 1 that fits the pattern available to us in terms of these data points, the red dots, to begin with. And we can throw in more data and the model will evolve, and then it will slightly tweak theta 0, theta 1 values, and thereby the lines will become like this or like that or like this or like that. Any of these lines will take shape based on what are the values for theta 0 and theta 1. And those are the two model parameters that we will tweak to come up with the best approximation available to us from the data that we have that will be a decent predictor of life satisfaction values, the Y values, for a country for which we don't have the Y value or the life satisfaction already known to us. And so that is where the prediction factor comes in. Basically, it calculates this value based on the input that we provide, because we will come up with B and M, theta 0, theta 1. And that's what machine learning model is doing for us in this example. So now, what we'll also do is identify how will machine learning help us come up with the right line. Is it this line? Is it this line? Is it that line? Or this line? We have no idea. actually visually we look at the data, you do have an idea, but that's visual. We don't want to be dealing with visual data like this. We want to actually have the machine do this for us and come up with sensible values on its own, for which we need to see how do we actually train the machine, how does the machine learn by itself. And the machine basically learns by looking at what I would call error. And this is what the machine tries to minimize, given all data points that it has at its disposal. And so if you have a system that has a lot of data coming in, what the machine learning algorithm will attempt to do is to minimize this. Or if there is a opposite of the same concept, it will try to minimize errors. Or the opposite of this will be to maximize utility or the benefit. So basically they're the same things. So you minimize the error or maximize the utility. Basically you're talking about the same thing. It's just flipping some bits. The concept is the same. And that's what we need to see, how the algorithms, all of these validated, absolutely every single algorithm will attempt to do these things. Either this or that, or maybe both. They're actually the same thing. Just a flip of a bit or a sign. It's a plus sign versus minus sign. That's it. That's the only difference. So every single machine learning algorithm, this is the goal, is to minimize the error or maximize the utility function. And so we'll now come up with some kind of a method of measuring. How do you measure an error of a given model? So let's do that visually in a sheet of paper, so we'll understand it correctly as to what is going on in terms of calculating error functions. An error function might sound complex, but they're actually not. Let's go see a graph, and I'm going to arbitrarily make something. And so here is, okay, come on, stop moving. Width. And there we go. So here's the graph. And what I want to do is maybe put some labels here, like that. And these are just your standard, standard graph paper. And we'll put some data points here. Like that. And the last one is actually not a data point. So there we go. So now we have these data points. Think of it as that's the data point we have. 1, 2, 3, 4. 1, 2, 3, 4. Now you try to put some kind of a model in the place. So let's go put some model. That's my model. Let's see the error function now. So I will like to now erase some of these unnecessary lines to help you visualize the error function correctly. Oh, I erased too much. Let's draw that back. Okay, so I was able to erase some of the unnecessary things that I did not need, and a couple more. What am I doing? Come on. Yeah. And the eraser is too thick. Okay. So now the line I had drawn was kind of sort of this. Now let's calculate the error. The error created by this line, according to these 4 data points that we have, are simply this distance, this distance, this distance, and this distance together. That's the error. If an ideal line was drawn, that is the best, and best means the lowest error, and minimize the error. That line will actually have the length of these offs, I should call them, what's the word for these kind of, they're called cosine. I'm forgetting the math functional name for this, but it's called perpendicular. I'll come up with a name. Basically, the distance between this point and that line, this has to be 90 degrees. That's the length you want to measure. And the measurement that you will need to do is actually, let me change the ink here. So this length, this length, this length, and this length. You want to minimize the total sum of these lengths. If your other line that you may have a different model, and the machine learning algorithm will constantly try to tweak the model itself until it comes up with a model that is the best model. And what constitutes the best model is the model that has the lowest error. That's the best model, or the maximum utility. That's the best model. So in our case, we want to minimize these perpendicular offsets, I would say, from the actual data point that we have. And that's one model. Let's draw another model with a different color. So here is a different color, let's say green. And I have another model that goes like this. And now we'll draw the colors in maybe another color here, orange. Yeah. And let's see from the point, this, and this little thing, and this little thing, and then this little thing. These are the 4 perpendicular items that I have. And if I make an addition of these 1, 2, 3, and 4 line lengths, I am able to conclude that this length plus this length plus this length plus this length is actually smaller than the other lengths that I have, 1, 2, 3, and 4. So you see visually what I'm trying to accomplish is trying to minimize the error. This is more than this. And so my line with a model that looks like this, and the error functions are actually lower, visually speaking, compared to the other model, which is this line. So that model is not a good model. It doesn't actually represent the data that I have with me. And so I should erase that model from my memory, and I don't use it. And this model looks a little better compared to the actual ideally fitting model, would probably be something that goes right through and minimizes any such length. Now, one thing I want you to be aware of is that in this length measurements in my visual representation do not account for the positive and negative signs, which are very, very important, which means that a line going in one direction versus a line going in the other direction are actually offsetting each other. So to address this problem, what we actually do is calculate the error function in a slightly different fashion. And I like to draw this in a picture form and also represent this in a mathematical representation for you to understand. The goal is for us to come up with a metric that measures these distances, account for the positive and negative offsets, and come up with an aggregate. There are at least 2 ways of doing these things. One of them is known as least squares, or rather simply root mean square, or square error, or RMS, or variety of names. But we'll get to that in a mathematical formula soon. And we'll understand that that is the function that the machine learning algorithm will try to minimize, which is, if you now look at an arbitrary point, data point, x1, y1, x2, y2, like that, and you have a line that goes, what you're really doing is a line that sticks you at x and y, and these are the data points that you have, x3, y3, like that. If you want to calculate the error function, what you will do is x minus x1, x minus x2, x minus x3, and you will end up squaring these guys. That actually defines your error function in one axis. You have the other axis also, y minus y1, y minus y2, and like that you will calculate the error and you'll square that, and that will be referred to as, and the exact model representation will come as we go forward. But that is how you would calculate a square error. That's one way to represent. The other way to represent the error function is to take a modulo value. So you have x minus x1, and you take a modulo value. So basically ignore the sign, whether it is plus or minus, you ignore that, just take modulo, and that's the absolute value that you will extract from the error. and use that and attempt to minimize this representation or this representation of the error. That's our goal. Ultimate goal is to minimize the error. And so that is what we are trying to accomplish. And that's what machine learning algorithm will do for us, and then come up with the optimal values of theta 0 and theta 1 in its simplest example here, which is the linear model. So some people also call the error function as cost function. And the function here, utility function, people call it benefit function. So cost, benefit, utility, error, whatever names you have, it's basically a measure of how good or how bad your model is. And that's if you do a training or a linear fitting. You can do this by the way, in Excel. Some of you, if you have done it already, you will see that this is called line fitting. Right click on a data sheet in Excel, draw a graph, scatter plot, right click on it and say trend line. And then it will show you a line. It will also show you this equation in some representation in what Excel will show. And it will basically come up with these numbers, theta 0 and theta 1. And that is what these values are. And the representation of the line, that is the least erroneous in terms of representing the actual data, but still keeping the line straight or linear. That's the model. How do you come up with these numbers, these values like 4.85 and 491? That is what training the model, the action of training the model. That's what this thing actually does. And we'll do this in a live example. So now the live example requires us to open that kit that we have running, Jupyter Notebook, which requires us to set up Jupyter and run it. So what I would like to do is take a moment to just walk you through steps needed to make your system run Docker first. So let me just write that thing down so that you have it handy for you. And I am here for you to, if you need help, you just chat with me on Slack, and I will do a video conference one-on-one with you, but I am just walking you through steps needed for us to begin functioning. The two-step process. First thing, get Docker running. Docker on Mac, Docker on Linux, Docker on Windows, 3 different animals. Mac, Linux, and Windows. That's a necessary step. And it is, strictly speaking, not necessary. You don't need to use Docker at all. You can just run scikit-learn and Python and matplotlib and all pandas and all the libraries that are under the hood. You need to set them up all on your own, which is, maybe some people like it. Like people like me, they love these things. So they'll do it by hand. Not everybody does it. And that is why we are trying to simplify the setup step. And I have already simplified it for you by creating an image, a Docker image. That image is already available for you to use, and we will use that image, by the way. And that is already configured for you. So what this Docker image is a Linux machine. Let me just show you instead of talking about it. So here, I will open my command line and go to the folder which has this hands-on machine learning. I'll make the font a little bit bigger so you can see. And this has the code right there. This is cloned from that repository. So cloning is, let me just show you the cloning aspect also. So here is GitHub, and here is the repository right there. And you have the clone link, and you copy that link right there. HTTPS, blah, 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 whatever that is. You copy the whole thing. Now bring it here, and you clone the entire folder locally. So you go to your home folder, wherever you want to work on, go to that location that you know. And in here, you say git clone, and then paste that link that you got from that location right here, this clone location. And then you have that repository located already. So when you hit that button, it will create a folder called hands-on ML. And that folder looks like this. That's what you see. That's the content of that folder. That's where we want to be able to work. The entire program uses this folder for us to operate. Now this has a subfolder called Docker. And so we can go inside that, and that's where you will find a set of tools to bring up the entire stack in one command. That command, I will write it down for you, but that uses Docker and Docker Compose. So there are two things that we need, Docker and Docker Compose. For some of you who are super familiar with this Docker business, like some of you are, I guess, you don't even need to worry about what am I talking about because you already know. So pardon me as I describe this, but we need Docker Compose. Docker Compose comes along with the Windows installation already. Docker for Mac and Docker for Linux does not. So you have to install it separately. So let's walk you through how to do these steps. So Atom Editor is where I will write these notes so that you will see what I'm doing as I type these things. And let's go type them. So you saw me git clone this. That will clone the repository. Then you go to hands-on ML. And then in that folder, you go to Docker. That's where you have Docker folder containing all the code that we need. But that's where you will work. Now to bring up Docker first, you need to go to hub.docker.com, or rather Docker for Windows, search for this. Search for this phrase, Docker for Windows or Mac or Linux, like that. No, not for Linux. Docker for Mac and Docker for Windows. Those are two products. Or Docker for Mac. And then you install. There is a package available. You double click and install. You need to create a login account these days. I think Docker doesn't let you download without a login. So if you go to Docker, get started, products, Docker desktop, and Docker for Mac, Docker for Windows, they're available. You just download them. And before you download Docker for Windows, this is the critical part, which I need to walk you through. Docker for Mac is fairly simple to just set up, just get Docker, and it's one binary, and you just done with it, you're done with it. But you, of course, need to log in. So that account is necessary. It is a free login, by the way. Now for Windows pieces, there are a couple of things to make sure that you are taken into account. And those are, first thing, Docker for Windows. It is a package. I think it's an MSI package. So that MSI package, Microsoft installer package, is what you need to obtain from Docker website. Once you install this package, it will do a bunch of things to your system. One of the issues that you will run into is that if you're using VirtualBox, you are stuck. And you're stuck because this Docker for Windows uses Hyper-V. So the problem is that you need to run Hyper-V to run Docker. And if you're using VirtualBox, then you need to uninstall VirtualBox, reboot your machine, and then enable Hyper-V. That's a gotcha. You will have that gotcha. If you have participated in a Cloud Genius Cloud Bootcamp, you probably have VirtualBox running already. And what does that mean right now? It means that you need to remove that virtual machine. You need to get rid of VirtualBox, because without that, you cannot run Hyper-V, which is a necessary component for Docker for Windows. It will not run. It will get stuck, and you will be, wondering what's going on. That's one of the biggest gotchas. So uninstall VirtualBox, and then you proceed with. So first step, uninstall VirtualBox. It's a necessary step, and reboot. Now, after having done that, you can now install that Docker for Windows package. Install Docker for Windows. In the process, it will install Hyper-V. Install Hyper-V virtualization engine, and this is not super intuitively clear as to what goes on. But in Windows, there is a little checkbox to start on Hyper-V services. So if you don't see that checkbox, don't worry. Probably Docker for Windows will do it for you. But if it doesn't, then you have to make sure that Hyper-V is running. I think I should write like make sure Hyper-V is running. And you can check that. You will notice that if it is not running, Docker will not function. So it's as simple as that. If it is not working, your Hyper-V needs to run. So you have to go system services and enable Hyper-V and then reboot your machine, and then Docker will eventually run. Basically, Docker needs Hyper-V on Windows. That's one necessary requirement. The second requirement is that Docker needs file system access. And the third requirement is Docker needs network access. So you need to give permissions for Docker to access your file system in Windows, and you need to give Docker permission to access your network. Because these things are online programs, they will go to the web, download data, download whatever we need, and then we'll use that. So these are the essential steps necessary to simplify your life, to get Jupyter notebooks to work with this entire collection of libraries, because the rest of the steps are intuitively simple. The rest of the steps are as simple as go here and then edit Docker compose YAML file. And in that YAML file, you will find references to hands-on ML. Let me just show you that Docker compose file so it's easier. I'll just make that edit for you. And so that file needs to be edited, and you have to make a reference to Cloud Genius. That's pretty much it. And Cloud Genius / hands-on ML. That's the change you will make in line number 16, and I'll just walk you straight to that point. And so here is our library. So we'll say git diff. Oh, there are lots of diffs. Okay, let's go simplify this and go quit at code. No. Visually, I want to see where is that? Where did I put it? I'll just manually show it to you. So the changes I made are this line here, line number 10. You need to say, or rather image name here, line number 11. Here you need to say Cloud Genius /. That's it. That's the only change you need to make in one place, in one line, in one file. And then you say Docker compose up, then you're done. So the change you want to make is right in line number 11 in the Docker compose YAML file. And then it will start using the image that I have created for you. And that looks like, so the change you will make in edit line 11 and make it look like this. And after that, you run Docker compose up -d. And then you're done. It is running. Once it is running, you open up http:// hello. There we go. So http:// localhost 8888. And then you log in as Cloud Genius. And then you're done. You will see what I see here. Where do I see it? Here. That's what you will see, the interface. It looks like this. And the entire Python notebook, Iron Python notebook with the index file, machine learning notebooks, a bunch of things will pop up, and you can just do whatever you want with TensorFlow, scikit-learn, matplotlib, pandas, and a ton of other things loaded up already. They will be functional for us. We'll be able to use these things, and that's what we will be doing Thursday, 4 p.m. And I will let you know that I am stopping to record. I am here If you need help with Docker, just ping me. We'll fix it if you get stuck. But these are the steps. And I will paste these steps. I keep this handy. If you get stuck, call me. It should be intuitive. If you don't have this VirtualBox thing, it is a breeze. But many of you actually have that VirtualBox. That's the problem. So you uninstall it and then reboot. And then it will be a breeze. Docker for Windows will walk you through everything needed. And once Docker runs, you clone this repository, make an edit in line number 11 that basically inserts the word Cloud Genius in the image name. Then you basically get the image that I have created for you, and you bring it up and you're done. You're functioning at that time. That's what I want you to be able to do. If you get stuck, call me, text me, Slack chat, video conference, whatever you need. And with that, I'm stopping record.